Welcome back. This will be lecture 6 of EC253C. We have been discussing about the programming model and various instructions associated with 8085 microprocessor. I have my last time we discussed a couple of instructions like add, move immediate. I have my programming model here. There are registers, accumulator. We have already discussed how accumulator is very essential to the microprocessor, to 8085 microprocessor. How every operation is performed with respect to accumulator and result is also stored inside the accumulator. And then we have flag registers, flag register, which we have not discussed so far. General purpose registers B, C, D, E, H, L, stack pointer and program counter. Before moving on to discuss some more instructions, let us discuss this flag register. What exactly is this flag register? It's an 8-bit register, we know that. And usually its bits are set and cleared by the processor itself. I will explain what that means in a moment. Let me draw it separately. Flag register, 8-bit register. 8 different bits. Each bit has a different function. For example, we call this 8th bit sign bit. Let me write an S. After that we have a 0 bit. We call it a 0 bit. Bit 6 is not used, unused. Bit 5 is auxiliary carry. I will write AC. Bit 5 is also not used. This bit is something known as parity. This bit is not used, and the last bit is known as carry bit. So 3 of the bits are not used. This bit not used, not used, not used. We have 5 bits with different names: sign bit, 0 bit, sign bit, 0 bit, auxiliary carry, parity and carry. So what's the function of these bits? As I have told you last time, that these things are set or cleared. That means either 1 will be written or maybe 0 will be written in any of these bit positions, and that depends upon the arithmetic results what we get in the accumulator. For example, if we are adding two numbers like 1 1 0 1 0 1 0 1 0 1 0 1 1 1 1 1, these are two numbers, we are adding it. I have loaded the contents. Maybe in accumulator I have written moo, or not moo but moo immediate, accumulator. This value, the first value, what's the first value? It will be 1 2 4 8 9 10 11 12 13 10 11 12, the ABC. It will be D, I think it is D5H. So accumulator will get, when this instruction is executed by the processor, D5 value will be stored in accumulator. That's, I will get a D5 here. And then the next instruction, maybe I will write something like this: add, or before adding I will move the second operands, the second number, move immediate in some another register, maybe B. write this is F1010 will be FAH. So in B I will get FA, and then the third instruction, well, this second instruction will be executed, this number FA will be copied to register B. It's simple. And then maybe I have third instruction, which is something like this, add B. What will third instruction do? It will add the contents of register B, the contents of register B, that's FA, that's this number, to the contents of register A, to the contents of accumulator, that's it will add this number to this number and store the result in accumulator. What will we get? For example, if I add this manually, I will be getting 1 1 1 1 1 1 1 0 1 1 1 0 1 1 1 1 1 1 carry. I got a 9-bit number, so I have a carry, and the result, and what will be stored, but only the first 8 bits, lower LSB 8 bits will be stored in accumulator. That is, and this number is, accumulator will get this 12 CF. So accumulator will get CF. Here we get CF. After the execution of this instruction, accumulator will be, but there will be, but this is not the correct result. This actually, by adding this number and this number D5 and FA in hex, we are not getting CF, we are getting 1 CF. But since our accumulator is only 8 bits, it will only store result of 8 bits. But the programmer or the processor should note that the result in accumulator is not correct. So how does it do that? Because there's a carry, the carry bit in flag register will be set, that is, and automatically 1 will be written here. Before the execution of these instructions, these 3 instructions, all the bits, all the registers and all the bits of all the registers are having 0. That accumulator will have 0, flag register will have 0 0 0 0 0 0 0 0. Similarly, register B, C, D, E, H, L, they have 0 0 0 0 0 0 0 0, 8 zeros. Everyone has 0 and 0 0 and 0. If I write in hex, it will be 0 0 here, it will be 0 0 here, 0 0 everywhere. But when I execute the first instruction, D5 value will be copied in accumulator. That's, I will get a D5 here. And after the execution of this second instruction, register B will get FA, and after the execution of third instruction, we will have CF in accumulator, CF in accumulator, and also carry bit of the flag register will get 1. That means flag register will have, if I write in binary, 0 0 0 0 0 0 0 1, or in hex, that is equivalent to 0 1. Not only this carry bit, but other bits will also accordingly update themselves. For example, first I will discuss this auxiliary carry. Auxiliary carry means if during an arithmetic operation there is a carry from bit D3 to D4. We count from 0, D0, D1, D2, D3, D4. If there is a carry from D3 to D4, in our case, when we are adding 1 0 means 1, 0 1 1, 1 0 1, 0 1 1. There was no carry from D3 to D4. That means auxiliary carry bit will be 0 here. Similarly, what is this 0 bit? If the contents of the accumulator after performing an arithmetic operation is 0, for example, I am adding or subtracting 2 such numbers that the result is 0, then this bit will be set, indicating that the result stored in accumulator is a 0. And then we have parity bit. What does parity mean? You might have studied about parity encoding and other schemes in your digital electronics. Parity may be of two types. It's even parity or odd parity. These are error detection and correction schemes. So what does even parity or odd parity means? Even parity means that the result or the data, we always have to maintain that the number of ones in a particular data is even. For example, this number of ones here in this 8-bit number of 1 2 3 4 5 6, that means it has even parity. Similarly, in this number 1110 0001, number of ones is 1 2 3 4, again this number has even parity. So again, let me take an example of odd parity number. Number of ones is 5, so parity is odd here. So what does this parity bit do? It checks the parity of the result that is stored in accumulator. When I add two numbers, for example, I added the above two numbers, these two numbers, the result in accumulator was 1100 1111. So number of ones in the result was 6, that's even parity. And in case of 8085, if we get an even parity number in the accumulator of a particular arithmetic operation, this parity bit is set, it will get 1. That means after the execution of this add between these two numbers, not only carry flag will be set, but also parity flag will be set. That means actually we will get a number 000101 in the flag register. That means 0 and 5. That means we will have here not 01 but 05. Similarly, the sign, this last one, this is for sign when we are adding two signed numbers. So if the result is negative, this bit is set. If the result is positive, this bit is cleared. You should remember that these flag setting or clearing of flags, this is done after every operation. So if I do one operation and maybe my carry flag was set, after that I do another add operation which doesn't generate any carry, so that will be automatically cleared. So we have to check, if we want to check these, we have to check them after every arithmetic operation, maybe addition, maybe subtraction. In case of subtraction, this carry flag is set if we have to borrow a 1. That means we are subtracting a larger number from a smaller number. In that case, this carry flag is set in case of subtraction. So for sum, this carry flag is set when we have a carry at the end of in the most significant bit, and in case of subtraction, if we need a borrow in the during the subtraction of the most significant bit. This will be more clear if you do a couple of examples. I may pause here for a couple of minutes and let you do this operation. There are two numbers, maybe I have to add 3a in hex and 23 in hex. So I write the program and then I have to see which flags are set and which flags are cleared. So 3a will be, you may do it yourself. You can pause the video for a couple of minutes. For a couple of minutes you can pause the video and then do the manual addition and see which flags should be set and which flags should be cleared in the flag register. Okay, let me do it. 3a 0011 a is 1010, A is 1 0 1 0, then we have 2 0 0 1 0 and 3 0 0 1 1. When we add these numbers 1 1 1 10, 1, no auxiliary carry here, no carry from D3 to D4, so my flag register is here. This was sign, this was let me write it here. This was sign 0 not used, auxiliary carry, parity carry, so no auxiliary carry, so this bit will be 0. I will assume that since we are not dealing with signed numbers, both the numbers are positive, the result will be also positive, so this bit will be signed bit will be also 0. And then let us continue with the addition 1 1 1 10 0 0. So I didn't get any carry, so that means this bit also will be 0. Now I will check for parity. How many ones are there? 1 2 3 4 5 ones in the accumulator. This result gets stored in the accumulator by default, 5 ones, so that means odd parity. And if there is odd parity, odd number of ones, then parity bit will be 0 also. All the other bits will be 0 because they are 0. We didn't have a 0 here in the accumulator, we have a non-zero number, so this bit will also be 0. So at the end of the operation, accumulate flag register will get 0 0 in hex. One more example we will try to do here. Maybe I have a number like 0 0 1 0 1 1 0 0 1 1 1 1 0 1 0 0. So let me add these two numbers. Again I will see what will be the contents of my flag register after this operation. 1 1 1 1 1 0 1 1 1. Oh, there's a carry from D3 to D4, so auxiliary bit will be set. That means we will get 1 here, so 1 here, 1 here, 1 here, 0 here. We didn't get any carry at the end in the MSB, so the carry flag will be 0. This bit will be by default 0. Parity, number of ones, 1 2 3 4 5 6, even number of ones, so we will have 1 here to indicate that the number of ones in the result is even. We have 0 here because it's unused, 0 here, unused, 0. We have a non-zero number in accumulator, that means we will have 0 here. This bit will only be set when we have a 0 in accumulator. And then signed, we are not dealing with signed numbers. Again we have a positive value, that means for positive value we will have 0 here. So and at the end of this operation, our flag register will have a value of 1 4 in hex. You can try many more examples from book. This is a very important concept, and in future lectures you may see how these flags are important. In fact, they are used for a lot of operations, knowing when we have a 0 in accumulator, knowing when we get a carry in accumulator or an auxiliary carry, even parity. Very very important bits. You may not understand the importance in this class, maybe in this lecture, but in future lectures when we write complex programs, you will come to know the importance of setting these flags by the processor. You should remember, these flags are not set by the programmer, but automatically set or cleared by the processor after execution of each instruction. So moving on, let's discuss a few more instructions. We have already discussed move, immediate, and add. Let's discuss few more instructions here. A brief recap. Instruction format. Oh, sorry. Instruction format. By now you are well aware of the instruction format that's used in 8085 microprocessor. We have something like this. We have each instruction, the general syntax is something like this. We have an opcode that actually tells what to do: copy, add, move, subtract, and or anything else, any operation that tells actually yes, what the operation is, or tells the processor or tells the arithmetic logic unit what the operation is. And plus we have something that we call as operand. It is actually the data. Why to get the data on which we have to operate? Why to get the two numbers we have to add? Why to get the two numbers we have to subtract? Or maybe why to get the data, where from to copy the data, why to copy the data. Or maybe if there, in some cases there might be a single operand. For example, if you are complementing a number, why to get that number which we have to complement. So why to find the operands, or what the operands are. Sometimes the operands, as you may have seen in the last lecture, sometimes operands are present in the instruction itself, and sometimes they are present in some registers, or you may see in this class sometimes operands are also present in memory. So how to find these operands? Are they present in the register, or they present inside this instruction, or all the in or all or are they in memory? So different ways. So here the second part tells us about these operands. So the instruction is opcode plus operand. Like we have seen in last class, we did something like this: move BC. So this is opcode part and these are operands. And also we also discussed about 5 different types of operations, and this one was in data transfer operation, a data transfer operation. Or another example of data transfer operation was move immediate B56. One of the operands here is immediate, is itself written in the instruction, or I can write move immediate accumulator 23H. In this case, a decimal number, the binary equivalent of this 56 will be transferred to B, and in this case we have written a hexadecimal number. Again, the binary equivalent of this hexadecimal number will be written in A. There are other data transfer instructions. For example, in some cases we have to transfer data from the memory, or we have to store some data in the memory. I have already told you that in case of 8085 we can have a maximum of 64 kilobytes. And our memory is numbered something like this. If I write in hex from 00, if we have 64 kilobytes, we might have a smaller amount of memory than this. This is the limit, 64 kilobytes. And the memory locations are referred with numbers ranging from 0000 up to FFFF in hex. Okay. And in this memory, I have told you there is program, the opcodes plus operands are stored here. And apart from this memory, apart from this program that we need to execute, we might have some operands, some data inside the memory. And if we want to, for example, starting from memory location 1000, This the memory location 1000. We have some data. We have maybe marks of students. 53. In memory location 101 we have some other number 46. There are some important constants maybe we have stored. How to retrieve that? And now we have to do some operations on this data. Maybe we have to calculate the average of these marks. So what are the operations we need to execute for retrieving, for getting these this data from memory to inside the processor? Or during some operations we may add two numbers, we may multiply two numbers, and then we need to store the data inside the memory, because registers inside the processor they only hold the data temporarily. If we need to store it permanently, we might have to save it inside the memory. So how we do that? We have two instructions, one for loading data from memory and one storing the data inside the memory. We have LDA. The opcode is here LDA. Load into accumulator. What to load into accumulator? Then we have the operand. For example, I may write the address here. Load 1000H. What does this instruction do? This instruction will load accumulator with the contents of this memory location 1000. In this case, this number 53, which is actually already written in the memory location 1000, will be transferred to accumulator. That means this will be transferred to accumulator. Here I have my accumulator and 53H. These are again in hexadecimal. Everything here is in hexadecimal. We will follow that 53H. Or I may also write as LDA. Maybe after this instruction I am executing another instruction, load 1001H. So this will actually copy the contents of memory location 1001H. This instruction, when this instruction is executed inside the processor, what will happen? The contents of memory location 1001 will be transferred to accumulator. That means accumulator will get 46H. Similarly, sometimes what we need to do, we need to store the contents of accumulator inside a particular memory location. We have another instruction, that is store. STA, store the contents of accumulator, and then we give the address, for example 2000H. So whatever is in accumulator, that will be written, in fact copied to the memory location mentioned here, in this case 2000H. So maybe I have a memory location 2000, because memory location, these are hexadecimal numbers. Memory locations are from 0000 up to FFFF. I have a memory location 2000. So whatever is accumulator here, now I have 46 in accumulator, and when I execute this instruction, this 46 will be transferred, will be copied to the memory location 2000H. 46 here. We will revisit these instructions when we write programs. We have discussed a lot of data transfer instructions. I have also given an example of arithmetic instruction add. Similarly, we have an arithmetic instruction subtract b. Again, as was case in add, when I said add b, it means add the contents of register b to accumulator and then store the result in accumulator itself. If I write something like this, add c, the contents of register c will be added to the contents of accumulator, and the result will be stored in accumulator. Similarly, in case of subtraction, when I write subtraction, I can write any register here, subtract b, subtract c, subtract d, subtract e. What will happen? The contents of this register will get subtracted from the contents of accumulator. That means this instruction will mean A contents of accumulator minus contents of register B, and this result will again be stored in accumulator. Similar as was case in add. Subtract register, the contents of this register, this can be any general purpose register, will be subtracted from the contents of accumulator, and the result stored in accumulator. Then we have logical operations. Okay, one more thing. This is add. We also have add immediate and subtract immediate, ADI and SUI. So in case of add, we mentioned a register and the contents of that register were added to the contents of accumulator. But in case of add I, the general syntax is something like this: add I, and we give it an 8-bit number. For example, add I 23H. So in this case, this number 23 will be added to the contents of accumulator, and the result again stored in accumulator. And in case of subtract immediate, we again, for example, subtract I 12H. So this 12 will get subtracted from the contents of accumulator, and the result stored in accumulator. So this is the difference between add and add immediate. In case of add, one operand is present in accumulator, but another is present in the particular register we mention in the instruction. But in case of add immediate, one operand is present in accumulator, but the other operand is mentioned in the instruction itself. Similar is the case with subtraction and subtract immediate. So now logical operations. An example of logical operation is AND. And the opcode here is ANA. In fact, here also we have two different ANDs. AND accumulator, this means AND accumulator, and then we have ANI, AND immediate. So how does this work? AND accumulator, similar to the add, but it will do the operation AND, logical operation AND. So I can write something like this: A N A B. So what will this instruction do? This instruction will logically AND the contents of register B with the contents of accumulator and store the result in accumulator. And in case of AND immediate, what will happen? The general syntax will be something like this: ANI and then a number, for example 21H. So what will happen? 21H will be logically ANDed with the contents of accumulator and result stored in accumulator. You should remember one thing here, that the flag register I discussed before, the contents of flag register will be set or cleared after every logical operation also. So if I do an AND operation, or maybe an OR operation, after the operation, processor will check the contents of accumulator and will accordingly set or clear the flags inside the flag register. So I mean to say that logical operations also affect the contents of flag register. Let me give an example here. For example, I have something like this. I have a small program, move immediate 54. Move immediate, I have to mention accumulator here. Move immediate accumulator, maybe any number, 54. I have already written 54H. And then, for example, I am ANDing it with some number, ANA or maybe this number is also immediate, or let me try to move it in some another register first. Move immediate D 82H, and then I am ANDing A and A, and A will accumulate the contents of D. So if I write this program inside into the memory of 8085 microprocessor, these 6 instructions will get executed one by one. Let me draw my programming model here. This is my accumulator, this is my flag register, this is B, this is C, this is D, E, H, L, and then I have stack pointer and program counter. So inside my memory, my first instruction is move immediate accumulator 54H. That means an hexadecimal number, the binary equivalent of this 54H, will get written inside the accumulator. 54 hexadecimal will be here. And when the second instruction will be executed, a number 82H will be written to the register D. 82H. So after this, what will happen? The contents of register D, when the third instruction will be executed, what will happen? The contents of register D will be logically ANDed with the contents of accumulator, and the result will be stored in accumulator. And at the same time, depending upon the result what is in accumulator, some of the flags, this flag register will get an updated value. In short, one thing you have to remember before I do the operation, there is something known as bitwise logical operations. What is actually AND? What does AND does? If we AND two non-zero numbers, the result will always be a non-zero. And if we add two numbers, one of them happens to be a 0, then the result will always be 0. That means if I add these two numbers 23 and I will do AND 56, the answer will be a non-zero number. Or if I do something like this, the answer will always be 0. In case of 23 and maybe 01, the answer will again be non-zero. But in case of 8085 A and A operations, what actually happens? The numbers are ANDed bit by bit. There's a bitwise logical AND. That means every corresponding bit is ANDed with its corresponding bit. Every bit is ANDed with its corresponding bit. For example, when in this case accumulator gets 54, 54 means 0 1 0 1 and 4 0 1 0 1. Then register D gets 82, 82 means 1 0 0 0 and 2 0 0 1 0. So when the third instruction is executed, that is AND D, the contents of register D are ANDed with A, but bitwise ANDed. That means each bit is ANDed with its corresponding bit. So if I AND the first bit 0 and 0, I will get a 0, 0 and 1, I will get a 0, 1 and 0, I will get a 0, 0 and 0, 0, 1 0 0, 0 0 0, 1 0 0, 0 1 0. So you may see I was ANDing two non-zero numbers, so logically I should have got a non-zero number. But since I am doing a bitwise AND, so each bit will be ANDed with its corresponding bit. So here I got a 0. So accumulator, and the result will be stored in accumulator. So the contents of accumulator will be updated, and we will have a 00H here. And also the contents of which register will get accumulated? flag register. What was our flag register? It was something like this. We had 8 bits. It was sign 0, then not used, auxiliary carry, not used, parity, not used, and carry. So not used, initially there were all zeros here, and these bits will not be changed. There was no carry, there won't be a carry in AND operation, and there won't be an auxiliary carry. The signs, we have positive numbers. We got a 0 in accumulator. That means we will have a 1 here. And also there are zeros. There are no number of ones in result. And 0 here is considered even. Not actually even, but it tries to make number of ones odd. So since we have 0 number of ones, so parity here will be 1. So our flag register will get a value 84. So 84. Is that clear? And similarly we have an operation that's known as AND immediate. In this case, I may have write this program, this small program, using AND immediate, and maybe I will say one instruction. I can write simply the first instruction will be same, move immediate accumulator 54H, and then I can combine these two instructions and write a single statement, AND immediate and the contents of accumulator with 21H. So what will happen? These two instructions are equivalent to these 3 instructions, because the first instruction will actually transfer 54H to accumulator, and here the second instruction transferred 82H to register D, and then D and A were ANDed. But in this case, the first instruction 54 will be transferred to accumulator, and when the second instruction will be executed, 21 number will be ANDed to 54. And again here the result will be stored in accumulator. The result will be same, all zeros, and accordingly various flags inside the flag register will be set and cleared. Similarly we have other instructions, also other logical instructions. We have or similar syntax, ORA or with accumulator, and we can write any register here, any register R, general purpose register, or we can have or immediate, and we can write any number here. Similarly we have ZOR, ZRA, we can have any register here, or ZOR immediate, we can have a number here. I think that's enough for this class. We will try to discuss some of the branching instructions in next class. Thank you.